to Scott. You're up next to talk about SAGE, open cyber infrastructure for the nation. So
cool. Let me do the deal. Are you able to see everything all right?
Yep, looks good.
Okay, well, first of all, thank you so much for having me back again. I apologize for being that guy that entered two abstracts in, but you know, open science is kind of one of my things that I'm very passionate about. So I'm here today to talk about SAGE, which is a software-defined sensor network, cyber infrastructure for edge computing. I'm going to show you a whole bunch of names. I am one part of a very, very large machine, but for those who don't know me, my name is Scott Collis. I'm an atmospheric scientist at Argonne National Laboratory. I'm also a senior fellow at the Northwestern Argonne Institute for Science and Engineering, where this project is actually funded through a grant from the National Science Foundation. So the names you saw before was our management group. This actually is our science team of young postdocs and junior scientists who are actually making the work happen. Many of you know Bobby, but you'll see work today from Bhupendra, Songha, Yongho, and Dario as well. But the folks who really make SAGE happen, and this is the one thing I want you all to take away from my talk. These are our cyber infrastructure engineers. These are the people who design the APIs, who build our data platforms, who make sure everything talks to each other, who build the code to actually make our edge compute hardware actually run. So they're not atmospheric scientists, they are computer scientists, and we could not be doing this without them. So you heard me briefly mention edge computing. What is edge computing? Edge computing is putting your compute up as close as is possible to the place in which data is collected or decisions are made. A supercomputer is a device for turning compute-bound problems into I/O-bound problems. For those of you who have used things like Cumulus 2, who are doing it in the data analysis world, know that inevitably as you start to ramp up in cores, unless you have a very, very nice fancy file system, or you're dealing with bigger files rather than lots of smaller files, you'll end up I/O bound. That will kind of limit your scaling there. Edge computing turns I/O bound problems into compute bound problems by being right up against the data source. You have near unlimited bandwidth, but you can't put an Aurora or a Summit next to a hyperspectral camera or a eddy correlation device. So the kind of idea we have in SAGE is this idea of a continuum compute, really embracing ideas within BER such as model-driven experimentation and digital twins and machine learning. And the idea is that we have all these sensors out in the field, everything from radars where decisions can be made, to neon towers, to hyperspectral images, old-fashioned lidars and the ones that actually collect point clouds. And we might want to make decisions there based on environmental conditions. Now, doing training at the edge is really hard, so often we'll actually send back packets of data when we have anomalous operation to supercomputing, train a network. For anybody who's ever worked in machine learning, one thing you'll know is that machine learning based models are really, really lightweight. You can train a model on, terabytes worth of data and end up with a megabyte size neural network. So it's actually really easy to move trained networks around. That's kind of the idea of the compute continuum. And so an example of edge compute type challenges, we have one area, by the way, that got this team really into edge computing was really privacy, actually. We had a bunch of cameras. We wanted to be able to image clouds, aircraft, ecosystem function, but we knew we didn't want to send back raw imagery. We wanted to send back data. We wanted to actually do the traffic flow calculations, your machine learning based detection of birds or coyotes at the edge and send the data back rather than the actual images. And so that's where the team really started to develop a framework for doing inference at the edge, as well as, and I'll introduce these soon, a bunch of bespoke hardware units that are designed to do inference and control at the edge. And that's where SAGE was born. SAGE is a multi-institution collaboration across the University of Chicago, Northwestern, Argonne, and folks like HP REN, which is a network of towers in San Diego linked to the San Diego Computer Center, the Chicago Array of Things product project, the Urban Wildlife Institute out of the Lincoln Park Zoo in Chicago, and one of our biggest collaborators is the National Ecological Observatory Network of the National Science Foundation, which we're really using as a test bed for rolling out all our instrumentations. Here's a little bit of background on the partner institutions. Here, AOT, we have a huge number of nodes across the city of Chicago to understand the intersection between, climate science and the cities who are impacted by climate science. Here's HP REN's network, real focus on wildfire detection, and I'll get to some cool stuff about that soon. And some folks here may know NEON, that is NSF's ecological network with sites across the US, including many sites that are actually going to be closely located with ARM's new extension into the southeastern United States. So our open hardware, our base cyber infrastructure is something called Waggle. Waggle is a technology that uses a controller board to synchronize several single board computers. Aaron very nicely introduced the NVIDIA Jetson. We also use Arduinos and Raspberry Pis, and we are working with new technologies to basically put them inside this enclosure that has been tested beyond testing down to minus 60 degrees Fahrenheit, blasted with sand and with water, so on and so forth, and with its thermals very carefully tested. And the idea behind this controller board, it can do things like flash new firmware, reboot, and do all the hardware management, as well as providing a software layer that allows new instruments to be plugged in. And I'll show an example of where we've been plugging in some nice aerosol instrumentation. That's the Wild Sage node. We also have a rack mountable solution we call the Sage Blade, which we actually have one installed in the Southern Great Plains as part of an ARM field deployment there, where we have one of our Wild Sage nodes and one of our Blade nodes, where we're actually doing a bunch of science there, including recently running our car detector to look at the impact of passing vehicles on an aerosol experiment recently. And here's an example of some work Bobby is doing. Bobby's actually using data from the scanning Doppler LiDAR and doing at the edge scene classifications on whether it's cloudy, clear, or whether it's raining at the same time. And Bobby has a paper he's going to be submitting soon on this, working with Rob Newsom and some other folks across the program. All of our, and I'll pop a bunch of links when I'm done into the chat, all of the code that does the inferencing at the edge is completely open source. And also we have a well-documented API, and we welcome new contributors to add code to our edge code repository in case they want to run code on the edge. And I'm going to step through several of the applications here. Songha Park and Yongho Kim have built a very, very nice neural network based approach that actually looks at basically total sky imagery and then uses, and we actually trained a network using that total sky imagery and downwelling radiation measurements to try to build a machine learning based photovoltaic estimator purely from imagery. And of course, I saw this and I said to Songha, this is amazing, forget the PV stuff, just do me cloud fraction and I'm happy. So we've been kind of building a an off-the-shelf, can run on any hemispheric camera, total sky imager cloud fraction product there. And this is actually in the press there in Atmospheres, and I point folks towards that publication there. Some work that Bhupendra Rao, a postdoc we have at Northwestern University, using both the total sky imager and our deployment at the SGP. He has actually been using optical flow to not only look at cloud cover, but cloud motion. And he's actually just about to publish a paper. It's actually just going through final review internally right now, where he's actually looked at the ideal integration time to get good results for cloud motion winds, and he's been working with Paitsa Maradian at Argonne, comparing those winds to the profiler based winds, and he will be submitting this very, very soon. So he's in the call today, so if there are any questions, I encourage you to reach out to him. Recently, we deployed a bunch of nodes to a mobile deployment of a NEON tower where they were doing a controlled burn. So this is actually one of the Neon towers. They had eddy correlation, 3D anemometer, upwelling, downwelling radiation, a bunch of instrumentations provided by Neon. But down here you see our SAGE nodes, and just across the side there you see a MET1 PM2.5 sensor that we've actually integrated in with our wild SAGE nodes. And up the top you also saw a thermal camera. We're really excited about some applications to wildfire. And here's some data hot off the presses from that burn from Bhupendra. This actually shows visible and thermal imagery from a Mobotics forward IR camera, and you can actually see the smoke is a lot higher temperature than the clouds. By the way, of course, I also just get excited by the clouds and being able to see the motion of the clouds in the infrared camera imagery. I think there is a lot of potential applications of thermographic imagery to the ARM program and the rest of DOE's atmospheric programs. Here is a plot actually Bhupendra sent to me this morning, and I said, hey, can I use this in the talk? This actually shows maximum temperature as a function of distance from the horizon that he manually plotted out here for different points throughout that controlled burn. And we can very, very clearly see the temperature impact of the smoke plume. This is super exciting because we know that a lot of our machine learning algorithms have great difficulty in just using RGBA images in differentiating between cloud and smoke. We also have birdsong detection apps and a whole bunch of other things, but I very briefly want to pop out of here and give you an idea of some of our open science side of things. So let me bring this up here. And Adam, I've got like 2 minutes left, right?
That's correct.
Right, so we actually have an API. So getting data from Sage is as simple as pip installing Sage Data Client. And I'm going to actually ask for data from that PM2.5 sensor from 19 to 23 UTC. And I can see I've got this thing called DFAQ. What is it? It's just a pandas data frame. So I can see what I've got there. I can see I have environmental air quality, concentration, and a bunch of values there. That gets stored in a pandas data frame. So what I'm going to do first of all is actually set the timestamp to being the date timestamp there so I can get nice plots. But then it's as simple as DFAQ dot value dot plot, and we can see what we get. And there it is there. So there's PM 2.5 in milligrams per meter cubed versus timestamp there. And I can plot that there and zoom in and actually get the data out of there. A bunch of other things that I'll put a link to this notebook here. I can actually download and look at the actual thermal camera imagery there. So for instance, there is a thermal camera imagery. So I do my XR, what is it? I can see I've got an X-ray data set with thermal image. So I can do like thermal image dot plot here. And I get a nice plot there with the image. I can see a couple of hot spots there. And I happen to know that in actual fact, frame minus 3000 here, so 3000 towards the end of that time step, actually had some nice fire returns in it just there. So I'll put links to all this, but you know, the take home I kind of want to give, and let me just stop sharing now so I can see everyone, is that Sage is there. It's open cyber infrastructure for the nation, and feel free to reach out to me if there's any interest in collaborating or working with us. Thank you.
All right, thanks, Scott. Are there any questions here? As Scott said, you can always follow up with him if you have interest or want to learn more. And Scott, you'll be dropping the links in the chat, right?
I will indeed. Thank you so much, and thank you everyone for your time.